The main topic in question was, do droughts cause an increase in carbon emissions in the Brazilian Amazon, even considering a decrease in deforestation? To do this, they tested what the drought's impact was on forest fire carbon emissions, keeping in mind deforestation reduction. They were able to accomplish this through collecting and analyzing sets of data such as atmospheric carbon monoxide levels. When they did this, they found that carbon emissions from drought-related forest fires are going to about 31% of deforestation fires. This means that the Amazon is entering a new land use and land cover change phase. The data presented in the paper shows us that the increasing temperatures have led to severe droughts in the Amazon forest. These droughts lead to more fire occurrences that add to the overall carbon emissions.
As we see in Figure 8, this leads to a dangerous cycle. This figure explains the connection between drought and fires in undisturbed forests. In Pathway 6, you can see how these fires make a loop back to climate change. Since there's more carbon dioxide in the air, you'll be trapping more heat, which raises global temperatures. The authors of this paper wanted people who keep track of carbon emissions to make policies to realize that drought-related forest fire carbon emissions are huge too, and they aren't part of deforestation. We see that reducing deforestation isn't going to do much in the grand scheme of things, and therefore we are able to understand policy needs to focus on non-deforestation fire more. Now that this knowledge is out there, we are starting to see changes in global initiatives, national policies, and local actions.
The authors addressed the question of whether the influence of drought-induced fires prevail over that of deforestation. And if so, does that mean that the reduction in deforestation rates will not lead to a direct reduction of carbon emissions? The authors analyzed sea surface temperatures, SSTAs, obtained from the NOAA to explain rainfall anomalies. Next, rainfall and maximum cumulative water deficit, MCWD, were used to quantify the intensity of Amazonian droughts, especially around the years 2005, 2010, and 2015, where the droughts were most severe. Satellite images from the INPE's Center for Weather Forecasting and Climate Studies was used to calculate the number of fire-hot pixels to show that spatial distribution of active fire incidents has increased also in these drought years. Maps of land cover with burned area from 2008 to 2012 were used to examine forest fires over the years with decreasing deforestation rates and also including the 2010 drought year. The authors also used INPE's PRODES data for deforestation from 2003 to 2015, as well as annual Amazonian biomass burning emission rates from MOPIT, measurements of pollution in the troposphere. Finally, CO2 emissions from deforestation and forest fires were taken from Brazil's Ministry of Science and Technology and Innovation.
If you look at Figure 3, you can see that figures A, B, and C show pixel-based annual anomalies of the maximum cumulative water deficit for 2005, 2010, and 2015 respectively. There has been a consequent enhancement of active fire incidents, and figures G, H, and I show active fire anomalies from 2005, 10, and 15. As you can see, the 2015 drought in C experienced significant negative MCWD anomalies in comparison to 2005 and 2010, with 2015 at 43% of the Brazilian Amazon biome, 2010 at 25% of the Brazilian Amazon biome, and 2005 at 22%. As a result, active fire detections in 2015 extended beyond the arc of deforestation, affecting areas of the Amazon that have rarely been impacted in the past. Now looking at Figure 4, you can see that in Figure A, the annual deforestation rate had a significant declining trend of 1,796 square kilometers per year. Figure C shows that there has been a significant decline in Brazilian Amazon carbon dioxide emission levels with a rate of 130.8 teragrams carbon dioxide per year. The active fire counts trend in Figure B, however, was insignificant. Figure E presents the relationship between the net LULCC emissions and MOPIT's carbon monoxide total column with deforestation rates. Analysis of this data shows that the estimated Brazilian carbon dioxide net emissions was strongly dependent on the annual area deforested, while MOPIT-derived carbon monoxide concentration was not.
As with most scientific studies, this data and its application is extremely relevant globally. According to the paper, the results can be used as an incentive to further emphasize South American governmental action to continue the decreased deforestation levels, manage farming and land use, and to have strategies to combat fires in dry years. Finding ways to stop drought-related fires are greatly important because CO2 emissions from the burning of biomass in forest fires will continue to add to the greenhouse effect, the trapping of heat in the atmosphere by certain gases such as CO2, whose structure allows it to move in a way that absorbs energy. Although Brazil Amazonian deforestation rates have been reduced by 66%, carbon emissions haven't decreased as expected. This is due to non-deforestation related forest fires, specifically drought-related fires, a topic that the authors hope will initiate governmental change to prevent such fires.